We can prove De Morgan's laws by showing that every element in one set is also an element of the other set. But let's consider another approach. Given two sets A and B, any element is either in A or its complement, and in B or its complement. And we can set up a table showing all possibilities, and then extend it to include all possibilities for the unions and intersections. So suppose something's in both A and also in B. We'll put a Y in these columns to indicate this. Since the element is in A, then it's not in A complement, and we'll mark that. And since the element is in B, then it's not in B complement. Now, since we're in A and also in B, then we're in the intersection. So we're not in the complement. Likewise, we're in the union, and we're not in the complement. So from the table, we see that we're not in A complement, and we're not in B complement. So we're not in the intersection of the complements, and we're not in the union of the complements. Notice that the element is in both A intersect B and A union B. Consequently, A intersect B is A union B. Or is it? This is only true if we're in A and also in B. But what if we're not? So it's important to consider all possibilities. So suppose we're in A but not in B. Then we're not in A complement, but we are in B complement. We're not in the intersection, though we are in the union. So we're in the complement of one, but not in the complement of the other. And we're not in the intersection, but we are in the union. And notice that the columns for A intersect B and A union B are no longer the same. And remember, if it makes a difference, it makes a difference. These two can't be equal. And remember, proof reveals we can identify what caused the difference. Something that is in A but not in B will not be in the intersection, but it will be in the union. There are two other possibilities. Something is not in A but in B, and something that is not in A and also not in B, and we can complete the table for such elements. Now, imagine we covered up the column labels. If it makes a difference, it makes a difference. But a difference that makes no difference is no difference. If we covered up the column labels, we'd see that the 6th and 10th columns are the same. So if we didn't know the column labels, we could conclude that they are the same. And since we do know the column labels, we have the complement of the intersection is the union of the complements. And again, proof reveals new insights. There's another pair of identical columns, and this pair of identical columns tells us that the complement of the union is the intersection of the complements. And put together, this proves what are known as De Morgan's laws. If A and B are sets, then the complement of the intersection is the union of the complements, and the complement of the union is the intersection of the complements. Again, we can use the proof to make it more clear why the complement of A intersect B is not the intersection of the complements. So our table shows they're different for something that is an element of one, but not the other. For example, if A is the set of people who had cake and B is the set of people who had ice cream, then a person who had cake but not ice cream is in the complement of A intersect B, but they are not in the intersection of A complement with B complement. And we can phrase that this way. Consider a person who did not have both cake and ice cream. That's somebody not in the intersection. This is not the same as a person who did not have cake and did not have ice cream. That would be the intersection of the complements, because they could have had cake but not ice cream. And that corresponds to this row of our table. Or they could have had ice cream but not cake, which corresponds to this other row of our table.